Assalamualaikum and hi. I'm Nur Aina Adrina binti Azman. Today I'm gonna present our group project for mechanics of material. We are from group 3, which we get the shape of equilateral triangle. Here is the introduction part. So in this project, our group had to construct a bar with a length of 30 cm and an equilateral triangle shape with 1.5 cm side length using uncooked spaghetti. We are required to test the strength of the bar by hanging a plastic water bottle and gradually increase the weight by batch adding 250 milliliter water into the bottle until the spaghetti bar is cracked and break apart. This is the objective of our project, which we aim to encourage students to apply the knowledge about stress and force calculation using the non-value got from the bar strength testing, such as the maximum weight of the load, to determine the maximum stress that the bar could bear.
The material used to construct the model is spaghetti with an average length of 26 cm, and for the model we have used cardboard to construct it. Besides, hot nail glue and strong glue was used to connect layers of spaghetti to form a triangular shape for the bar, and beside of that, a sellotape was used to further strengthen the connection. Let's move to the model part. The model was constructed using a paperboard. Initially, the base with the length of 30 cm and wide 2 cm was cut. Then, the triangular side with the length of 1.5 cm, which satisfied the requirement of the project, was cut. Next, the triangular side is connected on the edge of both sides on the end of the bar base using the hot glue gun.
Next, I will explain the model fabrication method. So the spaghetti stick were first cut into 26 cm and 4 cm length. So this is because the spaghetti stick we bought from supermarket were in non-uniform length. So in order to make it uniform length, we have to standardize each of the spaghetti stick by cutting them into 26 cm and 4 cm length. And then 8 spaghetti members were arranged side by side inside the molder and tapered to form the base layer. So this is the molder. 8 spaghetti members were arranged inside this molder and then form the base layer. Form this base layer which consists of 8 spaghetti members. And then similarly, the second layer was then placed above the base layer inside the molder using 7 spaghetti sticks and then tapered together. So this layering process is repeated by reducing number of spaghetti sticks for each subsequent layer. And finally at the top only left one stick. So this picture shows that every layer with different number of sticks. So these layers were finally bonded together using super glue and then tapered in staggered dry arrangement. So this arrangement is very important to ensure that this 4 cm part can be bonded stably with this 36 cm part in a cross manner so that it won't easily collapse during the load testing. So this is the product of our bar, and then as you can see from here, it has 30 cm long, and this picture shows it is the equilateral triangle with 1.5 cm height. Next, I'll explain the setup and load testing. So for this experiment setup, the model was placed horizontally between 2 support points. So as you can see from this image, and then an empty water bottle was placed at the center of the bar to act as a load point, and then water which act as a increasing load was gradually added into this empty water bottle, and then the water volume added start from 250 ml and then 500 ml, and then at the end 1750 ml. So at the moment it reached the for our log testing lah, at the moment it reached the 1750 ml, exactly, it suddenly collapses. So I will show the video of the load testing. Thank you very much.
Hi, I'm Vivni Lohining. I'm going to present our free body diagram and calculations. This slide shows the free body diagram of our spaghetti beam setup. We are evaluating a beam subjected to a uniformly distributed load W from its own weight, alongside a central point load P applied by a suspended water bottle. As shown on the left, the physical beam rests on supports at points B and D, leaving a 12 centimeter span between them and a 3 centimeter overhang on each end. To turn this into a mathematical model, look at the diagram on the right. We have isolated the beam and replaced the physical supports with upward direction forces, B and D. For this study, we tested incremental water volume starting at 250 milliliters to observe how the system responds under varying loads. This section details our equilibrium and internal force calculation using our baseline 250 milliliters setup as the primary example. First, we combine the weight of the beam and the water bottle to establish our total downward load. By applying static equilibrium, where the sum of all forces and moments equals 0, we solve for our reaction forces. Because the setup is perfectly symmetrical, the load is split evenly, resulting in 1.8843 newtons at both supports B and D. From there, we derive the internal shear force and bending moment equations across the entire span. While our experiment continued through higher incremental loads, testing at 500s, 750, 1000, 1250, 1500s, and up to 1750 milliliters, the calculation methods and steps for the rest of the lots remain exactly the same. Instead of repeating the math, we took the ultimate worst case scenario from our maximum 1750 milliliter lot, which yielded a peak bending moment of 1.0874 Newton meters at the center. This critical value forms the basis for our final safety analysis.
In this slide, the beam is subjected to 250 ml water load, which is the smallest load in our experiment. So the maximum shear force is about 1.83 Newton, while the maximum bending moment is 0.2045 Newton meter. Since the applied load is relatively small, the internal forces and bending are also the lowest. This slide serves as our reference point before we compare the beam behavior under higher water volume. Here, the water volume is increased to 500 ml. As expected, the maximum shear force increased to around 3.06 Newton, while the maximum bending moment also increased to 0.3517 Newton meter. And compared to the previous case, the beam experienced greater internal forces because of the heavy load. This shows that increasing the applied load causes the beam to resist more shear force and bending. For the 750 ml loading condition, the maximum shear force further increases to approximately 4.28 Newton and the maximum bending moment rises to 0.4988 Newton-meter. This indicates that as more water is added, the beam experiences greater internal stress and a larger bending effect. This trend is consistent with the expected structural behavior of the beam. This slide shows the result for 1000 ml of water, and the maximum shear force reached about 5.51 Newton, while the maximum bending moment increased to 0.646 Newton-meter. Both diagrams shows clearly that the beam experiences larger internal forces as the load increases, meaning the beam is bending more compared to the previous loading condition. At 1250 ml, the beam carries a heavier load, resulting in a maximum shear force of approximately 6.73 Newton, and the maximum bending moment also increased to 0.7931 Newton-meter. And this tells us that the beam is experiencing higher bending stress, making this a more critical loading condition from the earlier cases. For the 1500 ml loading condition, the maximum shear force increases further to around 7.96 Newton, while the maximum bending moment reaches 0.9403 Newton-meter. This is one of the highest loading cases in our experiment, showing that the beam is subjected to significant internal forces and bending as the applied load becomes larger. Finally, the slide shows the 1750 ml water load, which is the highest loaded tested. The maximum shear force is approximately 9.19 Newton, and the maximum bending moment reached 1.0874 Newton-meter, which is the highest value recorded. By comparing all the loading conditions from 250 to 1750 ml, we can clearly see the both shear force and bending moment increase as the water volume increases. And this confirms that a heavier load produces greater internal forces and a larger bending effect on the beam, which agrees with the expected behavior in structural analysis.
This brings us to our final structural verdict, determining the allowable normal stress. Using the geometric cross-section of our beam, we calculated its base width, moment of inertia, and the distance to the outermost fiber. Plugging our maximum peak bending moment of 1.0874 Newton-meters into the flexure formula reveals that under maximum load, the beam experiences a peak internal stress of 6.70 megapascals. To ensure structural safety, we applied a factor of safety of 1.5, bringing our minimum required material failure stress to 10.05 megapascals. Ultimately, this proves that as long as our uncooked spaghetti material can withstand a structural strength of 10.05 megapascals, our beam design is completely safe and won't snap under peak capacity.
In conclusion, our group successfully fabricated and tested an equilateral triangle spaghetti beam measuring 1.5 cm tall. During our destructive load test, the beam reached its ultimate limit at a maximum water volume of 1750 ml. When combined with the weight of the apparatus, this resulted in a total center load P of 17.90325 Newton. Our calculations showed that the maximum shear force reached a magnitude of 9.1870 Newton, while the maximum internal bending moment peaked exactly at center point C with a value of 1.0874 Newton-meter. We used peak moment to determine our final allowable normal stress by applying required safety factor of 1.5. Lastly, the reflection for this project that we got. So this project taught us how a triangle shape behaves under real pressure. We realized that careful fabrication is the most important part of building a strong beam. It was very interesting to see the spaghetti break at the exact point we calculated in our diagrams. This experience made the formulas we studied in class much more easier to understand.